Okay, I'm Keith Hall. I was born in Macomb, Ohio. It's a town of about 1,000 people in midwestern Ohio in 1918. My father was a hardware merchant and in addition carried on all sorts of activities like plumbing, heating, electrical wiring, some construction, and farm implement business. This was a kind of a rural community. In elementary school, it was about 50% mixed from kids that lived in town and kids that lived in the country. So my early years, I worked around the hardware store quite a bit and participated in one time or another in the plumbing gangs, the roofing gangs, the electrical wiring gangs, and all this, and putting together farm implements, delivering these things, and so I became acquainted at an early age with such matters as levers and screws and bolts and nuts. In fact, I counted so many of them at inventory time, I thought I'd never want to see another one again. But as it turned out, when I went away to college, this kind of experience was quite helpful in physics because I had had some first-hand experience in a practical way in many of the problems that we treated. Actually, I got interested. My interest in chemistry was greatly stimulated during my high school years by a chemistry teacher, Mr. Kramer, who, among other things, was endeavoring to put together a championship team to win a stateside competition. Well, we didn't win the statewide competition, but we did go part way along the way, and in the course of this, I got an awful lot of first-year college chemistry crammed into my head, and so when I did go off to the university, it was being lazy. It turned out that this was a easy pathway to follow, and so I majored in chemistry and minored in physics, and along the way I had, as I suppose most young people do, various aspirations, like maybe I should go into physiological chemistry, and I took a crack at that by taking the course in the medical school offered to the first-year medical students, and that convinced me right away that this area was not for me. It was too inexact. I needed something that was good to at least 1 decimal point. So I guess I could say that my career was guided a lot by fate or by dumb luck or whatever you want to call it. It just happened that as I graduated from the university, I wanted to hang around for several extra months during the summer to clean up various affairs around the university. So I took a course in explosives chemistry at Georgia Tech in the summer of 1940, and so when I then went to the ACS meeting looking for a job, we were not in war at the time, but war was going on in Europe. I thought, well, I'm going to take a job until the time comes for me to do my selective service, so I might as well make as much money as I can in the meantime. So I determined to take the job that paid the most money. Well, as it turned out, being green behind the ears, I got knocked around from this interviewer to that interviewer in the employment clearinghouse until I finally ran into a brash young man named Frank Long, who I had never heard of before, and he was rather guarded in what he had to say, except that he had a job he thought I was uniquely suited for. He couldn't tell me anything about it, but except that I had to undergo an FBI clearance before anything more could be done. Would I please hold up for a month before accepting another job? And so, having about given up on him, I was just about to go to Des Moines, Iowa to work with U.S. Rubber when finally this position came through, and it turned out to be a position here in Pittsburgh with the Division 8 NDRC, which is National Defense Research Committee. And they wanted to make use of my vast experience in explosive chemistry, you see, because this was set up under OSRD as an explosive branch to do research of benefit to the military, which we might need sometime in the foreseeable future. I never will forget my arrival in Pittsburgh where I was directed to report to the U.S. Bureau of Mines at 4800 Forbes Street. And when I arrived there, I was told, well, you were to report here, but really you're supposed to go about 15 miles out in the country to Brewston at the Bureau of Mines Research Center out there, which is now known as the Pittsburgh Energy Technology Center. They were building up some new small buildings there for people to do research on explosives of various kinds. When I arrived, I found there were only two people I could find on the lot. One of them was a tall, lanky guy, and he was sitting on top of a table with his feet up on the table and with his hands around his knees and his chin resting upon his knees, more or less. And he was talking to this portly gentleman over leaning against an adjacent table, and it turned out that I was the first of about 100 young men that reported to this new organization. And the two people I was talking with was George Kistiakowsky and Louis Hammond. Now, at the time, that didn't mean a damn thing to me. They were just two of the fellows, and it turned out that Kisty was quite a lively fellow. He was not married at the time, and he proceeded to like to go out with the boys on Saturday nights and live it up quite a bit. And so he and Frank Long and myself and many others, these young men from these divisions, used to go out places like the old Pittsburgh Hotel Henry, where they had a room where they had a pianist, and people did a lot of singing, and along with consumption of a local beverage, which is known as Fort Pitt beer, or Duquesne beer, and so we had quite a lively time. As it turned out, this group of people that were collected here included a lot of people who turned out to be very fine scientists, such as Frank Westheimer, who used to argue with me daily on the way to and from work about almost anything. It didn't matter. Whichever side I'd take, he'd take the other. And one day I said to him, Frank, I said, how come the other day when we were discussing this, you were on the other side? And he said, well, how do you expect me to learn anything? So I had this initial association with some very good people, and so it turned out that I never did get drafted. The assignment that we had, well, the laboratory had, was manifold, but the one that my particular compartment dealt with testing explosives for detonation velocities and shock waves and the shapes of shock waves and so on, and actually had the assignment that we didn't realize that we were putting together the requirements to trigger the atomic bomb, which was research was going on elsewhere, and our job was just to find a way to put it all together so you'd have an excess of the critical mass in one place at one time. And so when the thing finally did explode, we were informed what we'd been doing, much to the consternation of many of us. But anyway, at the end of this period, I decided to stay on and complete a master's degree in chemistry at Carnegie Institute of Technology, which I'd been working on part-time Saturdays and weekends and so forth during the war. And indeed, I finished this in 1948, and but at the same time, I had taken a position at the adjacent Bureau of Mines, and with under H.H. Storch in the Division of Synthetic Liquid Fuels, and my immediate superior was guess who? My good friend and benefactor of many years, Bob Anderson. And it was from Bob that I learned the elements of catalysis and the uses of physical absorption and chemisorption and trying to develop understanding of catalysts and catalyst structure, morphology, and so on, and the elements of the chemical kinetics, how it applied to the Fischer-Tropsch synthesis. Well, when I finished my master's degree at Carnegie Tech, I had the opportunity then to leave the Bureau and join the Gulf Fellowship at Mellon Institute under the wing of Professor Paul Emmett, which provided me a means of working on a degree in University of Pittsburgh on research that I would do under Emmett. And this was an exceedingly great opportunity, not only because of the opportunity to work with this very famous man, but also because of the people that he had the ability to collect around him. Very, very good people. And so, making a long story short, we did some tracer studies of the Fischer-Tropsch synthesis, and during this time we were studying these things, following up on the work of Joe Kummer, who initiated this work. Along came a friend of a lifetime, Dr. Richard Kokas, and he joined up and we became lab partners. And Dick was a really bright individual, and he had a great grasp of physical sciences. And I was at the time completing my thesis work and my coursework at the University of Pittsburgh, and I found out a very good secret to know, and that was that all you had to do was to tell Dick that this problem was beyond his capability of solving, and bingo, you could forget about it. The next day he'd have the answer for you. So that's how all of the really difficult problems got solved, the sticky wickets, you might say. And of course, in the course of discussion, when he would get the solution, I'd argue with him that it was all wrong, and having learned this earlier, that this is a way to learn, and proceeded to learn a great deal from him. At much to my dumb luck, I guess I would say, Paul Emmett decided in 1954 to leave the Mellon Institute to become Grace Professor of Chemistry at Johns Hopkins University. And my research work was just about the stage of completion. I had about 6 months more work to do, plus writing my thesis. And so Emmett left me behind to finish up the work and took Cocos with him to help establish his new facility at Johns Hopkins. And of course there were some other members of the group also remained. But when I did finish my thesis about 6 months later and got my degree, much to my amazement, I was offered to become Emmett's successor and rebuild the group that he had had at the Mellon Institute. And as I say, this is what's known as being in the right place at the right time, and this was where my career underwent a change from being somebody else's technician to actually having a research group of my own. So this stretched on for another 15 years, which I spent as senior fellow in charge of the catalysis research for Gulf Research at the Mellon Institute. In fact, until after the merger of Mellon Institute with Carnegie Mellon to become what's known as Carnegie Mellon University. At this time I had two options. I could have become part of the university, which they already had too many professors, which I didn't want to do with, or move my existing group to Gulf Research in Hartmanville, and I was told this would be just a change of address. But it turned out to be really a great change in atmosphere at the same time. In fact, I many times felt like a fish out of water, because people around me were talking about economic factors in the petroleum industry, which I knew nothing and cared less. So I gave this a whirl for about 30 months, and then another good fortune fell me in that I was offered the position of distinguished professor at the University of Wisconsin, Milwaukee, and I spent the next 13 years there. And this was, so I guess in the sum total of my career to date, I've had the great good fortune of working with some 70 young men for periods of time, shorter or longer periods of time, and these have led to many very long and lasting friendships. It's been remarkable since I moved back to the University of Pittsburgh here a couple of years ago. I've had repeat visits from people who have been were my one-time students who took their PhDs under me for a year or two for sabbatical leaves, and this has happened in 2 instances in 2 years. And so you can see the kinds of relationships that develop. I guess that is a thumbnail sketch of Burt, of the background, where I came from, and so forth that you asked me to give you.
Well, how do you now feel about the defense work being disguised as it was when you went to work?
Well, you got to understand, Burt, that at the circumstances under which this was occurring, you got to remember that we had at this time Hitler and Nazi Germany, and it was already known by the time that I joined up with this that they were having exterminations of Jews in vast numbers in Europe, and that Pearl Harbor came along in December of the year in which I joined up with this group in September, and that there was a mad rush to go and join up, and to be told that no, you can't do that. We've been requested to hold you out. If you insist, we'll take you, but we'll reassign you to your same job at less money. So, no, but at the time, we're talking about life and death situations. In the early couple of years, when under these contracts following Pearl Harbor, we faced one defeat after another in the Pacific as Japan moved southward. It was not till they got clear to Guadalcanal, which is just close to the coast of Australia, before they finally got slowed down to a halt and things started to repair themselves. And you could only think, and if you think about these matters, you got to think about them in context of the times and the propaganda, if you will, that we were given daily in news accounts and motion pictures and so forth that were made, which depicted the cruelty of the Japanese armies and the rape of the peoples they overcame, and the brutality and all this. And so when we discovered that we had, if you like, slaughtered a whole city or two, the first two atomic bombs, and then we discovered that we were partly responsible for this, I think our general reaction was, it serves the bastards right. Now, this feeling, I think, has long since passed, and I have never had any guilt complexes over it. I still feel that I'd rather see a couple of 100,000 of our enemies pass away than something like 1 million or so of our own young men in the conquest of the Japanese mainland.
Well, during that time, Brunauer was responsible for some research in Navy explosives. Did he ever come to where you were working, or?
Well, if he did, I don't remember that he did. I do remember others, like Linus Pauling, who visited a time or two, and there were a number of rather famous people came through, but I don't remember Brunauer at that time. I became acquainted with Brunauer's work mainly through study of Brunauer's book after I met up with Anderson after the war. And then I met Stephen personally in my interactions with the colloid division of the American Chemical Society, where there were a lot of surface chemistry and catalysis symposium in the early 50s, and so we became pretty good friends, and of course we had a common friend in Paul Allen, so I thought a lot of Steve. I visited him at Clarkson a time or two and so on, but I didn't know him at this particular point in time.
How would you describe Storch, or did you get to know him very closely?
Yeah, Storch was a wonderful person to work with. He was pretty positive about many things, but I found that he would respect you more if you if you really sincerely disagreed with him and you told him so. And this happened on a couple occasions. I remember that I hesitantly said, "Well, Dr. Storch, I hate to disagree with you on that, but I think if I were going to interpret this information, I think I'd reach a different conclusion." And he said, "Oh, what do you mean by that? Explain yourself." And but I thought it was a great compliment when he said, "Well, that's interesting. Maybe you'll look into that." You know. He was that kind of person. Actually, after I came to Mellon Institute, he was moved to Washington and finally elected to retire from the Bureau and became a more or less or part-time consultant of American Cyanogen. And a time or two he came by at Mellon Institute and would sit around and visit, and he would point out to me he was a little bit like Emmett in this respect. He always had something interesting to point out to him, you know. Maybe it'd be hydrogen diffusion through metals, or maybe it had something to do with the production of alcohols in the Fischer-Tropsch synthesis, or one thing or another. He was always very nice guy.
Well, how was he able to do so much administrative work and still stay so on top of technical matters?
Well, I suppose what it amounted to was that Storch had a very relatively small group of people working in what you might call the total area of synthetic liquid fuels during the late 30s and early 40s. But during the war years, it became pretty obvious that the Germans were supplying a fair portion of their motor fuels for supporting their war vehicles by Fischer-Tropsch and the Burgess process. And so Storch or one of his assistants or one of his colleagues made some back-of-the-envelope calculations and concluded that at the present rate of consumption, the world's petroleum reserves would be exhausted by 1978, and but there was enough coal, domestic supplies, to last, take care of our total energy needs for 1,000 years. This is what was told me when I joined up at the Bureau in '46. Well, this kind of argument persuaded Congress and the military, as a matter of fact, that we ought to do a bit better job of debriefing the German scientists after World War II than we'd done in debriefing them after World War I, where we came home with a barrel of synthetic ammonia catalyst and then spent nearly 14 years trying to reproduce it. And finally, as you know, Emmett and his group at the Fixed Nitrogen Laboratory finally unraveled the basic secrets of this. But and this they weren't going to have happen, so they proceeded to bring people like Helmut Pichler to the United States and plant them at places like the Bureau mines. And at the same time, they got busy and they appropriated a sizable sum of money at that time for the development of synthetic liquid fuels industry in the United States. And typically, they put the cart ahead of the horse, and they appropriated $7 million to build a demonstration plant at Louisiana, Missouri, and $1 million to establish a basic research effort in Pittsburgh, which was then to be headed up by Storch. So that Storch's group expanded from maybe half a dozen people or something like that to maybe several hundred people in a matter of a year or two. This was again a wonderful experience for me. I probably skipped over this part of it, but again, you had this vast, rapid expansion, and some of the people who appeared on the scene at this time, besides Bob Anderson, who I've mentioned, were people like Sol Weller, who's now a professor at
New York at Buffalo.
At University of New York at Buffalo, and Milt Manis, many years a professor at Kent State, people like Larry Hofer, Gus Friedel in mass spectrometry, and Irving Wender, who's now at the University of Pittsburgh, who I think you know very well, Milt Orchin, University of Cincinnati. All these really first-rate people, again, much a repeat of the World War II situation, where you have a bunch of new people all come together, all young, all have a lot of interesting backgrounds and ideas that they could exchange. There was a lot of little intellectual stimulation. In a period of the 6 years I was at the Bureau, the knowledge of the Fischer-Tropsch synthesis in the open literature changed from where you ran carbon monoxide and hydrogen into a converter at one end, and gasoline, alcohols, waxes, all sorts of strange compounds came dribbling out the other end. And in almost economic, marketable quantities. We also discovered, however, that you could start to make your synthesis gas with methane and end up with about 50% methane back, and this wasn't too economic. But interestingly enough, the whole thing came down to a vote in the United States Senate in 1954 on whether to go ahead with setting up a synthetic liquid fuels industry, and it failed by one vote in the U.S. Senate. At this point, and this is, I think, largely because by this time the petroleum companies had found these vast new reserves in Saudi Arabia and Libya, in the Pacific, Borneo, Java, places like that, and Indonesia. They and they really didn't see any reason to use resources and manpower, because no longer were we supposed to be out of fuel by, and we're talking about 1934 now, by 1978, but we had enough oil in sight to last until 2050, or at least. And this didn't count on any new discoveries we made. The only trouble was that Lord Almighty come along in 1974, and by golly, petroleum did start to get short after all. And so at this point, as practically everyone that you know knows, the government vastly stimulated research, again in synthetic liquid fuels, with huge sums of money, and there was a huge reinvention of the wheel, and very little other progress as far as I can see.
Well, was Storch just lucky in picking all of these good people, or did he have a great insight into people?
Oh, I think some people are talented this way, it also helps to enjoy a, a favorable set of working conditions that is generally known, and if the people that you already have employed, if you have a good nucleus of people, they will attract more good people. Besides this, Storch was very talented in knowing good people when he saw them, I think. That's the only thing I can say.
Well, did you get to know Pickler when he was at the mines?
Oh yes, Pichler and I grew to be good friends, and I recently visited his institute in West Germany. Pichler died several years ago, but I had many interesting discussions with some of his colleagues about his personal characteristics and so on.
Well, what were some of his personal characteristics?
Well, that's not easy to answer. He was he had a very deep and dogged interest in anything that related to the Fischer-Tropsch synthesis and its mechanism, and he knew everybody and everything that had ever been done in this area. He enjoyed very much walking and talking and discussing fundamentals of these processes. And I had, of course, we had 6 years work in Fischer-Tropsch synthesis at the Bureau, and then another couple of more years on the mechanism and using tracers and things like that, Alan and Mellon did. And so we had a lot to talk about.
Well, some people think it should be called Fischer-Tropsch Pickler. Did he resent not being included?
No, I don't think so. This would be very un-German. It's accepted practice in Germany is that you have a chair, which is held by somebody, and everybody who works in the same department is under this chair and recognizes this chair as the person he looks to for promotions, for support for his research, and so on. The German system is not nearly as democratic as our system here.
Well, how did he adapt to the American system and American life?
Well, he must have adapted all right, because he only had to stay a couple of years. He ended up spending, I think, 13 or 14 years in the States before he went back. I think this was fairly typical to a number of Germans who came over under similar circumstances. They stayed here and they worked as Fischer did for a while in the government laboratory, and then moved on into an industrial laboratory. And then in due course they were able to obtain an appointment to a chair, in West Germany, and whereupon they returned to West Germany, and this was, I guess, the thing that they had been waiting on all this time. Every German scientist's ambition is to end up in a chair.
Well, how did Bob Anderson and Storch interact when you joined them? What was their relationship?
Well, I would say Anderson reported, well, I guess something like this. On paper, Anderson reported to another gentleman who reported to storage. I don't recall even the other gentleman's name at the moment. But this was like one scientist talking to a civil engineer who reported to another scientist. And I don't think it took very long for this system to get bypassed. And in fact, Anderson succeeded Storch in directorship of the laboratory when Storch moved to Washington.
Well, how would you describe Bob Anderson when you started working for him as a person?
Oh, Bob was a wonderful guy. He had a group of, I guess, 4 main people, under which each of these had 1 or more people working for them. One of these people had about 20 people who ran a bank of test reactors. So there were something like 16 reactors doing Fischer-Tropsch tests all of the time. Okay, and these tests would run maybe 6 weeks, 2 months, 3 months, whatever was necessary to get the required data. You've got to remember too that in this period of time, the analytical facilities weren't what they are today. By any means, we didn't have gas phase chromatography. You could use mass spectrometry, submit samples to Friedel and his group, and we could get everything through C4. But from there on up, it was things like distillations, Podbielniak cuts, and more or less boiling point distributions, bromine numbers, OH intensities in the IR, and so on, to get product assays, which could be given. If you look at the literature of this time, there wasn't a whole lot of detail in it. In fact, this is one of the things that helped more than anything else to unravel the mechanism of the Fischer-Tropsch synthesis, was the fact that in the years right after World War II, 3 of America's biggest petroleum companies got busy and did a very careful analysis of the carbon number distributions all the way up to C16, I believe, or somewhere up in there. And with isomers and olefins and paraffins and the whole breakdown of things. And as this product characterization developed, it was discovered what's known as the carbon number distribution law, and then the isomer distribution law. And so it became pretty clear that this was not a cross-linked polymer hydrocracking into all kinds of fragments or anything like, which is one idea that was held at the time, but it was actually a simple set of polymerization steps, if you will, which followed something which resembled fairly closely the Schultz-Fleury distribution law, but it differed from this law in that, according to this, the Schultz-Fleury law, you simply have a monomer which adds on repeatedly and to get one more unit added to a growing chain. And this can only give you straight chain products or regularly branched chain products. Whereas in the Fischer-Tropsch synthesis, it became pretty clear early on that a single carbon fragment could add on to either the end or the next to the end carbon atom on the chain, and the chain would grow accordingly. And so already, as I started to say a while ago, in 1951 or 52, when this book, The Fischer-Tropsch and Related Syntheses by Storch, Golumbik, and Anderson, appeared in print, it was pretty clear what the mechanism was like, and the ideas about the reasons for this end and the next to the end addition was thought to involve condensation of hydroxyl groups, which has been fairly well discounted, I think, by this time. But basically the law hasn't changed regardless of what the single carbon fragment is. There's also been some evidence that it isn't just necessary that you have single carbon fragments, but you can have like a CI carbon number fragment adding to a CJ at random in steps like that. And this won't change your distribution very much because of the way the carbon number distribution drops off with carbon number in a logarithmic fashion, that the contributions from these things are pretty small. So you could have this and you wouldn't know it. And some people have pointed out that the possibility that certain discontinuities, the high carbon number, might be explained in this way.
Well, at that time, it seems to an outsider there were essentially two groups working on the chain growth predicting isomers, Weller and Manus, and
well,
then Anderson.
everybody was working on various aspects. We were also working on carbides, nitrides, and carbonitrides, interstitial phases, and their possible role in controlling product distribution, or their possible intervention in the synthesis, which thermodynamic work by Emmett and his group pretty soon showed could not occur. But the Wender-Orchin group were actually got directed towards hydroformylation chemistry. Okay, and this again, I imagine that Irv would tell you if you got him in the right kind of a conversation. At this time, there wasn't much known about carbonyl chemistry at all. In fact, inorganic chemistry was a very descriptive subject, and anything about carbonyls was something that only a few basic rules were known about. The rule of 18 was known, and interestingly enough, in the early work, first 6 months or so, when involved in this carbonyl chemistry, these organic chemists didn't realize that cobalt can't form a monocarbonyl. They were worried about whether it should be cobalt CO5 or cobalt CO4, and I think perhaps I point out to them what happened is you form a hydrocarbonyl or a dioctocarbonyl, and when they got this chemistry in their head, they were able then to deduce the rules of hydroformylation. But the most startling thing that came out of this work was Wender's discovery that he could substitute things like acetylene ligands for carbonyl ligands. And truly, this was the beginning of today's vast menagerie of organometallic chemistry. I think in 1946 and 47 and thereabouts, if you look back, there weren't any of these things known. But once these things that seemed like curiosities at first became known, inventive people and curious people started looking at just what all kinds of organic ligands could be involved in these things. The whole development of modern inorganic chemistry, I think, probably followed from Wender's work at the at the Bureau of Mines. And this has had a profound effect on our understanding of how metal catalysts should work and so on. I think it's still true that except for a few isolated exceptions, that homogeneous catalysis will never play a major role in production of fuels and bulk materials, but certainly it's helped us an awful lot in understanding catalytic reactions and in some specialty cases like L-dopo production, or in the case of making acetic acid from ethanol, things like that. There are a couple of examples where the theories have formed the basis of important industrial processes.
Well, how did Bob Anderson interact with his group when you were there?
Oh, well, we had a weekly meeting. And at the weekly meeting, each of the 4 group leaders who worked under him reported on what they'd been doing and what they found interesting. And Bob always encouraged that this thing would develop into a discussion, and a free-wheeling discussion as to what each of us thought about each other's ideas, the Bureau of Mines under the Civil Service was a curiously relaxed place to work. You see, it was. In fact, when I left, I really hated leaving. It was just such a nice place to work. The famous tale was told around about, I think, about. After we were kind of established in Fischer-Tropsch synthesis, the Navy came along and they wanted us to see if we could find a catalytic synthesis for hydrazine, which they thought would make a good jet fuel, high-energy jet fuel. And indeed it would. But their thought was, well, you could synthesize ammonia, why not hydrazine? There were no thermodynamic data at the time, and so in good spirits, under Anderson, we set out to try to synthesize hydrazine. Well, everything we tried didn't work, because as we discovered in due course, making some statistical mechanical calculations, this was thermodynamically unfavorable to go from hydrogen and nitrogen to hydrogen. But along the way, we had some practical jokers who decided that they would stir things up a little bit by putting some real hydrazine into a test bottle that was a result of a particular catalyst that they were testing at the moment. And after this was sneaked in, and after the test was run and the test dye was put in, lo and behold, it showed a beautiful test for hydrogen, as expected. So the chemist who was doing the work grabbed the flask and ran into Anderson's office and said, "Look what I got." And they spent the rest of the afternoon figuring out just how and why this might have happened. That night, just before I left, Anderson said to me, he said, "Storch will really be interested in this." Whereupon I said, "Bob, I'd take this slowly if I were you. I think you better repeat that test." He says, "Why?" And I said, "Well, there's a vague possibility it might have been tampered with." And he said, "You bastards." Yeah, it was just a interesting little thing that happened there.
Well, was that the extreme, or were there a number of instances during the course of 2 or 3 years that would happen like that?
Oh, I think we were forever playing practical jokes on each other, but usually not tampering with data in this kind of way. There were all kinds of funny things happened that I can recall. I don't know whether if any, certainly no scientific in it. One of these was somebody packed a piece of pressure tubing full of dry ice and put a pinch clamp on one end and a pinch clamp on the other end, but you didn't tighten until the last minute, and attached a piece of lead to the device. And when one of us distracted the janitor by pointing at a spot at the ceiling and so forth, well, the other guy typed this up and dropped it in this bucket of water, you see, and so the thing sunk to the bottom, but about the time the guy turned around to his bucket again, the water was coming up in the bucket. And his eyes got big and he looked down, the water started over the top of the bucket, and all of a sudden, boom! The pressure tubing broke and water flew all over the place. I never will forget, this fellow just simply ran down the stairs and got in his car and went home. We didn't see him for 2 or 3 days after that. Oh, that sort of thing happened. And in another case, there's a guy that always was sitting in his car waiting for the whistle to blow, so at the quitting time. So one time then we sneaked down and jacked up one of his rear wheels and put bricks under it, so it was just about that much off of the ground. So about 10 minutes before quitting time, he got down and got in his car and started the motor. I didn't warm up until the whistle blew, whereupon he proceeded to step on, put it in gear and step on the accelerator, and the rear tire went roar. And of course, all of us knew this was going to happen, so we were all standing around clapping. Oh, we had lots of good time. I think some of those things still go on. We used to have these regular picnics and so forth. And really had a wonderful time working at the Bureau.
Well, now, when you joined Emmett's group, were these kind of pranks and things still?
Oh, we didn't have time for. We were really exceedingly busy going to graduate school and so on. I suppose a few comical things did happen in the course of these several years there. One of them I remember is that we had these furnaces that were heated through a tyrotron circuits, DC circuits. These circuits were fed by polarized plugs. If you got if you had the proper polarization and you put them in as you were supposed to, everything was fine. But if you reversed the polarization and you touched the furnace, you'd get a good 110 volt shock. So one time, one of my colleagues decided that he owed Cocos one, and so he switched the polarization of this. You've seen these BET systems all made out of glass, you see, and Cocos went down to pull up the furnace around his apparatus. He got poked and the furnace kept right on going up towards the ceiling through all this glassware. It was a horrible mess. And, you know, those kind of things we thought were funny at the time. I don't know whether those kind of jokes would be funny in the modern world or not. You got to remember, maybe you remember this, I don't know. In the old days on Halloween, we didn't go trick-or-treating, we just went tricking. In the Depression years, nobody had treats, so we made up for it by soaping windows, making rackets, upsetting back houses, and all sorts of interesting kind of things. So I think it was a different world, different atmosphere back in those days than perhaps you have today.
Well, how did you come to join Emmett? Did you get to meet him before this?
Oh, well, see, Emmett came to Pittsburgh about 47 or so after when I was working with Bob Anderson, and Bob was had been a postdoctoral student of Emmett's during World War II, working on gas mask charcoals and other things. And so, yes, I met Emmett early on. He was here, and he and Anderson were lifelong friends. And so, I think that what happened was I owe to Bob Anderson my opportunity to work with Emmett. Joe Kummer was leaving. He'd been doing this interesting work on the chain building mechanisms using radiocarbon, and so Emmett needed somebody to carry on that work, and I think Bob just plain told Paul that I would probably be better than any PhD he could come up with, because I already knew practically everything that Joe had been doing, but I didn't. As I discovered when I got there, and Paul took me and said, "Well, no, this is Joe's apparatus. You see, and he did this kind of work." And he said, "All you have to do is to start out with radioactive acetone and carry on." See, and well. Joe was one of these kind of people who never cut anything out of a rack when he put it on, so he had layer after layer on this rack, and to begin with it wouldn't hold a vacuum, and secondly I couldn't figure out which pathways he'd used. So yeah, that was quite interesting, getting that thing up and running again. I essentially cut it down and rebuilt it, so we got it working.
Well, did you get to meet Comer? And
oh yeah, I knew Joe before he left town. You should get Joe on tape sometime. He was a fable at the Mellon Institute in the good old days. This guy was just unbelievably bright, and also very advanced in his thinking. Social, okay. Nothing derogatory, except that he felt if it was hot in his laboratory, he didn't see any reason why he couldn't work in his underwear. And this was out of tune with the dignity of the institute in those days. And well, you know, Joe had earned a reputation of being an outstanding scientist, but one of those that you read about in the paper, you know, a little far out, which of course is not true.
Well, he did a lot of awfully meticulous research.
Oh, very clever. If you consider the research methods that were available at that time, the inventiveness of Joe in being able to solve just some practical problems of getting the molar radioactivity of olefins and paraffins separately, and analytical procedures for separations of hydrocarbons, and many things like this. He was extremely inventive, and he left Mellon Institute to take a position with Dow, and then he moved on to Ford Motor Company. If you talk with Mordecai Shaleff and his colleagues at Ford, they will tell you that they've never met anybody that was more clever in his approaches to research than Joe.
Well, Kokis was another one who was clever. When he came there, had he worked other places when he came with Emmett, or was that?
No, he came right out of a doctor's degree, which he'd taken with Frank Long at Cornell. He knew nothing about catalysis and was almost a little reluctant to start in on such a different tack. So he became my lab mate at the time, so what Emmett had decided was that maybe Emmett wanted to get into an examination of the Dowden theory of electronic effects in catalysis, which came out in 1950 for the first time, and it gradually gained increasing interest in the years, the subsequent years. And so when I at about 1952, where Cocos appeared, Emmett wanted to get into this, and he determined that, he told me, he said, "Now, you don't have to do this if you don't want to. This is Emmett." And you probably know him well enough to recognize it. He said, "You don't have to do this if you don't want to. If you want to stick with the Fischer-Tropsch synthesis, fine." He said, "I really think that if you could make some progress on evaluating and understanding this Dowden theory," he said, "you'd make a much better PhD thesis than what you're doing, because what you're doing has been already, the cream's been taken off of the crop. I got a lot more I want to do, but you're going to be, just the next guy in the line of, and I think it'd make a more attractive thesis work." So I got busy and made up a series of copper-nickel alloy catalysts, and we repeated the hydrogenation of benzene and the hydrogenation of ethylene. Dowden had done the latter, and Russell and Best and Russell had done the former at Williams College, I believe. No, what was it? Williams College? Anyway, it was this, Burt, it was this Brown University. And Emmett was very attracted to this work because making a small change in composition of these catalysts, according to Best and Russell, would make a change in activity of maybe 10 to the 2 or 10 to the 3 in catalytic conversion. And this is a methylene hydrogenation. So we undertook to have a look at these things. And the thing that we did that Dowden didn't do was we got activation energies and frequency factors out of the data. And Dowden's nice, neat theory blamed everything on changes in activation energy brought about by changes in work function plus contact potential at the as you change the composition of the alloy. And this didn't look too unreasonable at the time, because if you call the work of oh gosh,
in Germany?
No, here, that's the guy that Otto Bake.
Oh.
The work of Otto Bake showed a whole series of different evaporated metal films in the hydrogenation of ethylene. All had the same activation energy, and they differed they would go through a 5 orders of magnitude in activity as you change it. And this is a matter of frequency factor. Well, whereas Dowden's stuff was all blamed on activation energy differences. So we were early on in the alloy work, which showed the kind of correction that the Dowden thinking needed to be required. Okay. So anyway, the tune of things changed over the next several years, from where people moved away from trying to attribute changes in catalytic activity in electronic factors from bulk properties of the crystal to surface properties of the crystal. And many of the things that Dowden observed were due, as we know now, to the change in the surface composition rather than copper and nickel, rather than changes in bulk composition.
Well, when you took over the group at Mellon, how did you select the people that came to join you?
Well, I inherited the ones that Emmett had left, and this was a great learning experience. I had been working and playing jokes and golf and having a lively time with these same fellows for several years, and we were all equivalent, and I more or less figured that would the way things would change. And moreover, I made a great mistake in thinking that whatever I thought was probably agreeable with them too, because I thought we all thought alike. And it didn't take very long to discover that each and every one of them had their own different basic requirements for what they wanted out of life and so on. But Emmett was a good teacher in many ways. It all works out if you govern your actions in such a way that you be as helpful as you possibly can to the people who work under you. And you're always in there. You always do whatever you can to advance advance them in any way you can. You find that everything works out fine, and you end up with good friends, even though you're sitting in the seat where you first find a bit uncomfortable.
Well, how did you get involved with the Journal of Catalysis?
Well, along the way, I guess I had met Pierce Selwood probably at the Gordon conferences in Northwestern, and I acted as a referee for a large number of his papers. I used to get about one or two a week, I guess, and I don't know. He never told me why I was selected, except that when it came time for him to step down, I was approached and told that I was offered the opportunity to become editor if I wished to do so, period. And Frank Stone, of course, was the co-editor with Selwood, and so he became co-editor with me. Yet our offices work completely independently, and we don't even have quite always the same policies. We try to put forward a more or less uniform front, but I'm sure our attitudes change a bit.
Stone had taken over as the other editor, and so you never worked with Du Bois.
Yeah, Stone had taken over as the European editor when what's his name?
Du Bois?
Du Bois stepped down. Du Bois stepped down.
And that was before you took over.
Yeah.
How did you get involved in the Catalysis Society?
Oh, that went way back. In 1956, we had the first International Congress in Catalysis. This was largely organized by the Philadelphia section, and Heinz Heinemann was really a central figure in this organization. And when the thing was all over and done with, it was decided to hold a second Congress in Paris 4 years hence. And there was some leftover funds, and there was a question about how these might be handled. You know, it wasn't proper to hold them in someone's private account or something like this. And so Heinemann and Burt Farkas and I and I think probably Bob Burwell or Val Dennis or somebody, got together at one of the ACS meetings and discussed the possibility of setting up a national society, which was to have as member clubs, the catalysis clubs, the Chicago Catalysis Club and the Philadelphia Catalysis Club. And the Pittsburgh Catalysis Club was just in its formative stages, you see. And so, actually, what happened is I don't know exactly who, Heinemann or Farkas or somebody, got together a set of bylaws, and we decided to spend $100 or something and go to a lawyer and see if we could incorporate the thing in the state of Pennsylvania, since this is where the money was being held. And so for a long time we held that the office of the Catalysis Society, the official office, was at the University of Philadelphia, University of Pennsylvania in Philadelphia. And you know, one society formed after another after this, until now we have 10 or 12. But it all started just as a fact that there were two successful clubs already in operation. There was several $1,000s that needed to be handled in some way or another. A vehicle was needed, and so by merging 2 or 3 clubs and making provision for the addition of others, and some simple bylaws, and setting up a mechanism for approval of these bylaws by all those present saying aye, the society came into being. I believe, wasn't it so that Alex Mills was elected the first president of the society? And Alex did his good deeds too in taking steps to establish a tax-free status for the society, and tightening up rules and regulations so that we had some meaningful way to operate, and so it's all evolved from that, and mainly from the fact that the national meetings are a great success because you meet everybody you want to see at one place at one time.
Well, at these meetings, scientific debates are one of the purposes to have them. One of the ones you must think that you were involved in, a memorable one, was with Herschler.
Oh, yeah, Al Herschler and I had a running debate for several years, I guess. You know, one of these things where it turned out we were both right and we were both wrong. We had, when Emmett left the Institute, Harry Lefton and I, wanted to change course a little bit so that we wouldn't be, because we didn't know quite what Emmett was going to do at Johns Hopkins. We didn't want to know, except we thought we'd polish up the work that he was doing. And Lefton had just arrived, he hadn't really got started in much of anything. So we decided to look at the possibility of forming stable carbenium ions on catalyst surfaces using triphenyl carbonyl, which we figured would react with protons to form triphenyl carbenium ions, and water, which of course happens. But then one day, Harry decided to look at triphenyl methane, mainly because Don McIver was finishing his thesis with Emma at the Mellon Institute, and it dealt with the chemisorption of isobutane on cracking catalysts. I'm sure you've probably heard this story before, but he was finding small but definite chemisorptions. And the chemisorbed isobutane would exchange with deuterium groups on the catalyst up to 9 in number, but not the tertiary one. And so it was reasoned that the tertiary one was conserved, and so we thought maybe being held by a Lewis acid site and then put back onto the molecule desorb. And so this is one of the great lessons of my lifetime. We thought we had eliminated all other possibilities, and so this hydride abstraction had to follow by because it was the only thing left. We found that hydrogen was not formed, olefins were not formed, olefin impurities were not responsible. What else? Well, the problem was finally solved by one of my students by the name of Xingyang Wu, came along several years later and discovered a very simple sort of thing that triphenylmethane reacts like a little bit like cumene. You make benzene, and that gives you the diphenyl carbenium ion, and this then takes away a hydride ion to form from triphenylmethane to form diphenylmethane and the more stable triphenyl carbenium ion. Well, Herschler had all along thought that this must be wrong, and he and I agreed that the carbonyl would react with the proton to form the acid. So Herschler seemed to find that he could oxidize the triphenylmethane fairly easily in contact with air, very much the way that cumene can be oxidized to form a hydroperoxide. He thought was the source of the activity. Well, it turned out that only works in the presence of light. If you excluded light, that didn't happen. So we went merrily around and around on this argument for a long time until finally it turned out that I found out that we found out that we got the real answer in our laboratory, proof positive. So this was the year that Kokus was chairman of the Gordon conferences. So I said, Dick, I want to have time for a quickie, 5 to 10 minutes. He says, what about? I says, I'm not going to tell you. It'll be a surprise. So Kokus introduced me as the mystery presentation of his conference. Even he didn't know what I was going to talk about. So it happened. Al Herschler had a bad case of diarrhea that day. So I got up and I said, well, I really want to tell you, I want to give you the final solution of the Hall-Herschler debate. So let me first of all tell you what this is about. But before I go any further, I know Al isn't feeling so well, so Al, don't worry too much. I want you to stay for the whole thing. I said, this won't hurt. So then I described what I did to you a minute ago, and I showed, the equivalence in the amount of benzene and diphenylmethane and triphenyl carbenium ion that are all formed by the reaction mechanism which I described. And so that settled the whole thing. There was no longer anything to argue about.
What do you think that debate between you caused you to work harder and to accomplish more in that area?
Oh, I don't know. I suppose it did in a way, in that it was, we both had our necks stuck out pretty far, and neither one of us was very anxious to be wrong on this. And so I was gratified when it turned out that we both were right and we both were wrong in some of our aspects of the whole thing. But I think that the thing that intrigued me about this more than anything else is you know, the first time that when Lepton first produced these visible spectra, which we could record and see that the spectra was exactly the same as you get in sulfuric acid solution, triphenylcarbonyl, and you knew from other work in, say, liquid sulfur dioxide that you had conductivity measurements, and you knew exactly what this was. There was no debate about it. And we were interested, interestingly enough, this debate had certain interesting spin-offs that helped us to get into other kinds of things. One of these was the formation of cation radicals, which was actually the Rooney and Pink were the first people to publish on this, and to my great chagrin, I discovered that I had a paper that had been submitted to the Journal of Physical Chemistry, which was rejected on the grounds that this work had just been published. A little bit too late. But on the other hand, if you read Rooney and Pink's original paper, they state in it, in the introduction, that our presentation at the Second International Congress on Catalysis, where we thought we had demonstrated this ability, the ability of these catalysts to remove hydride ions, their electrophilic character, challenged them to look at molecules such as perilene and anthracene, and discover that indeed they did seem to pull electrons off. I think so. Oh my goodness, there was a year or two in there when we had lively go around among Brower and co-workers in the Shell laboratories, and Rooney and Pink, and they extended their work over to aluminas, and they discovered with the aluminas very interesting stuff that not understood today yet even. That alumina plus triphenyl chloride or trityl chloride or triphenyl carbonyl will not form these ions. You put perilene on, and they won't form cation radicals either. But if you add oxygen into the system, they will. And moreover, if you double the pressure of oxygen, you get twice as many. And I don't know that this that this is entirely understood at present, even today. There's work in the literature that shows that if you do this in liquid solutions of acetic acid, trichloroacetic acid, and so on, that here too, in the presence of oxygen, you can get these radical cations formed, but the acidity of the solution very much changes the ability to form these ions, and I don't think anybody really understands that either. But for a time there, we thought that perhaps that this electrophilic character was doing lots of things, desirable things, catalytically, and finally everybody reluctantly concluded that no, the only thing it could do is maybe make Coke.
Well, you mentioned the international meeting. What sort of changes have you noticed over the years in the international meetings, if any?
Well, I don't think, I think maybe this is just symptomatic of old age or something, but I don't find them nearly as exciting as they were in the early days, and possibly because we know a great deal more about catalysis these days. And we don't see exciting new breakthroughs like Eichen's use of infrared spectroscopy, which was going to be the cure-all for all ailments, and has been a tremendous asset indeed. We've had one tool come along after another nuclear resonance, electron spin resonance, ESCA, XAFs, NEXAFs, SEXAFs, and so on. And each of them adds a bit. But there's no one common solution to all of these problems in catalysis. And I still believe in the dictum of Herman Pines that if you want to understand catalysis, you got to study a catalytic reaction. And the old Burwell paradox that if the molecule's too simple, you can't learn anything. I think that's a good place to stop, because I think that by the time I get where I'm going, that's about all the time I can do.
Let me just get your most satisfying bit of research, and then we'll stop.
Oh, boy, that's very difficult.
That's too complicated for a simple answer?
I suppose if I had to pick one thing, I would say it was the paper by Ederhoven, Christner, and Hall on the hydrogen Y zeolites, which showed us for the first time what a Brunstad site really is and how it functions in aluminum silicate. I suppose that is probably the thing I enjoyed most. But again, I think that I've enjoyed life as a catalytic chemist because of its vast variety of techniques and things you can do. You never get bored doing the same old thing. You maybe become a bit of a jack of all trades and maybe a master of none, but you got plenty of specialists around to work with. And I don't know, I think that catalytic chemists, as a rule, are all nice fellows. You don't find a sourpuss in the lot. I'm not saying that all quantum mechanicists are difficult people to get along with either, but I think that we enjoy the open debate, the freewheeling discussions we have, and the personal interactions that we have, and we enjoy seeing the whole field grow as opposed to a small part of it. And I think that it's been a wonderful